Hello everyone and welcome to Vibrations in Acoustics. Today we're going to work a little bit with force vibrations. So here we have a simple example of a weight on a spring. The spring has a constant of 4,000, a weight of 50 newtons, and then we have a harmonic force applied to it. So basically a sinusoidal force going back and forth pulling on this that has an amplitude of 60 newtons and a frequency of 6 hertz. And we'll talk about this in a little bit. But the three things we're trying to find is the extension of the spring due to weight, and then the static displacement of the spring due to max applied force, and then the amplitude of the force motion of the weight. These first two are actually really easy, because even though they're worded a little bit differently, they mean the exact same thing. You want to find the extension of the spring due to just the weight, and then you want to find basically the displacement of the spring due to just the force at its maximum point, so at its maximum amplitude basically. So let's go ahead and solve for A first. This is really easy. You know that force for a spring is equal to kx. Well, in this case we're looking for the extension of the spring, so it's going to be force over k is equal to x. So if we do that, we've got 4,000 all over excuse me, not 4,000, the weight 50 newtons divided by 4,000, which was going to give you 0.0125 meters. And that's the extension of the spring due to just the weight. So you've got a weight on the end of a spring. Pretty easy. And then for B, well, now you have the force of the forcing function. Now with this, a normal applied force, F of t, usually takes the form of F naught sine of omega t, where F naught is the amplitude of this function, but that amplitude is the maximum force of this forcing function. So in this case we have a maximum force of 60 newtons, and the omega is 6 hertz, which we'll have to do a conversion on when we use that a little bit later. But this is the force that you're using in this part, because that is the maximum force applied by this sinusoidal function, pulling on it, pulling on it, pulling on it in a sine wave manner. Okay, so then, using this the same equation up here again, you end up with x is equal to F naught over k, which is going to be equal to 60 all over 4,000. I'll put in the units here, 4,000 newtons per meter. Meter comes back up, newtons cancel. And if you solve that out, do the calculation on that real quick, you'll get 0.015 meters. And this is the displacement of the spring based on the maximum force applied by the harmonic forcing function. Now basically what you can do is add these two up at the maximum point, and you'll find out what the maximum amplitude of the whole thing would be at any given time from just the normal spring sitting there. But usually when you're working with weight hanging from a spring, you neglect the weight in harmonic excitation, because if the weight is sitting there on the edge of the spring, that's its static equilibrium. So you consider the point of static equilibrium the place where you then measure amplitude from for the actual forced motion of the weight. So finding the amplitude for the forced motion of the weight, we're going to use just 2 or 3 equations that hopefully you've been introduced to. We have omega. We know omega is equal to 6 hertz, which is equal to 6 cycles per second, which we need to do a conversion on, because we know that we don't want cycles, we want radians per second. Well, one cycle is equal to 2 pi, because one cycle is a full circle around this around the period of the harmonic function. So you do 6 times 2 pi and you'll end up with 12 pi radians per second as equal to omega. So we've got that. Now we need to find omega n, the natural frequency of the system, without any of the forcing functions on it. So omega n is equal to the square root of k over m. We have k, we can get m from the weight, so this is going to equal a square root of k, which is 4,000, divided by, the weight is 50 newtons, 50 newtons divided by 9.81 meters per second squared. And this will give you, this is basically the mass by taking the weight and dividing it by the acceleration of gravity. Make sure that encompasses all of that. And if you solve that out, you'll get 28.0143 radians per second. Okay, so we have omega and omega n. Now the reason we wanted these is because in order to find the amplitude of the force motion of the weight, when you're working with force motion, you can basically jump to this equation. Basic force motion on a mass, force motion on a mass. You can jump to this equation for the amplitude, which is equal to x of delta st all over 1 minus r squared. Sorry. 1 minus r squared. And 1 r squared, r is equal to omega over omega n. So that's why we had to find the omega n and the omega, because we are using them to solve for r. And delta st is actually equal to this x up here. This can be contributed as delta st, which is equal to f naught over k, which we have right here, as you can see, which is the force F naught over k, which is delta st, which is this upper st. So then this is equal to, since we solve for this, we've got 0.015 all over 1 minus omega over omega n, which is 12 pi, all over 28.0143 squared. And if you solve that out, it will be 0.0185 meters is your maximum displacement, maximum amplitude for the force function of the weight.